morning friends. After the discussion of the MCQ question asked in Neet and All India PMT and also JEE, today we are discussing the MCQ question asked in Physcis. Now the first question that is asked in mock test in 2006, the mass of the photon in motion is, what is the mass of the photon? Already we know that from the properties of photon, the mass energy of the photon is equal to hf, and according to the Einstein's equation, E is equal to mc square. Therefore, E is equal to hf and E is equal to mc square. Comparing these two equations, therefore mc square is equal to hf. Therefore, mass m is equal to hf upon c square. Therefore, the mass of the photon in motion, that is hf upon c square, already given as the option B. Again, the first question of Physcis that is asked in mock test of 2006 taken by the board, the mass of the photon in motion is, we know that according to the properties of photon, energy of the photon is equal to hf or hc upon lambda. And from the Einstein's mass energy relation, E is equal to mc square. Therefore, mc square is equal to hf. Therefore, m is equal to hf upon c square. That is our answer. Now the next question, also asked in 2006, what function of material is 4 electron volt is given? The maximum wavelength by which the photoelectric emission can be obtained. The work function per meter phi is 0, where the phi is given the 4 electron volt. What is the maximum wavelength which can produce the photoelectric emission? We have to find out the lambda. Now, for that purpose, we know that work function phi is equal to hc upon lambda 0. Therefore, lambda 0 is equal to hc upon phi. Actually, we require the threshold wavelength. The minimum or the maximum threshold wavelength is required to produce the photoelectric emission for given work function for electron volt per meter. For that purpose, lambda 0 is equal to hc upon phi. We substitute the value lambda 0, Planck's constant 6.6 into 10 is to minus 34. C is the velocity of light in vacuum, 3 into 10 is to 8 upon work function phi is given the 4. Now listen, work function is given in electron volt. Now the hc is in joule, so we have to convert the work function into joule. Therefore, 4 into 1.6 into 10 is to minus 90. Therefore, lambda 0 we obtain in meter, that is 3.103 into 10 is to minus 7 meter. Now, what answer is given in nanometer? Therefore, we have to convert in nanometer. Therefore, 310.3 into 10 is to minus 9 meter is equal to 310 nanometer. So that is our answer. Again, for a given material, work function is given the 4 electron volt. Now the maximum wavelength by which the photoelectric emission can be obtained. So equation of the work function phi is equal to hf0 or the hc upon lambda 0. We require the value of wavelength lambda 0. Therefore, lambda 0 is equal to hc upon phi. Value of Planck's constant 6.6 into 10 is to minus 34. C 3 into 10 is to 8 upon work function 4. But work function is given in electron volt. We have to convert into joule. Therefore, multiply by 1.6 into 10 is to minus 90. Thus, we obtain the answer is 310 nanometer. Clear? Okay. After that, the next question asked in 2006. A proton accelerated by the potential difference of 100 volt, having de Broglie wavelength is lambda 0. Now the alpha particle accelerated by the same potential difference, its de Broglie wavelength will be. Now we know that here the accelerated voltage is given and charge of the proton or the alpha particle also we know it. Therefore, de Broglie wavelength lambda is equal to h upon p. Lambda is equal to h upon p is equal to h upon under root of 2m with a q. 2m. Now, for alpha particle or the four particles of this equation, we can know that the h upon 2mv voltage are given the same. To accelerate either the proton or the alpha particle, both are accelerated by the same potential difference of the 100 volt. Therefore, h, 2 and v are constant. Therefore, de Broglie wavelength is inversely proportional to the mass into charge. Therefore, alpha is proportional to the 1 under root of mass into charge. For alpha particle or first derived for the proton, so 1 upon under root of mp and e. And for alpha particle, lambda alpha proportional to the 1 upon under root of m alpha e alpha. Now for alpha particle, mass of the alpha particle is 4 times the mass of the proton, and charge of the alpha particle is double than the charge of proton. Therefore, lambda alpha upon lambda p is equal to mp ep upon m alpha e alpha. Substitute the value. Therefore, mp ep upon 4mp, because the m alpha is equal to 4mp and e alpha is equal to 2ep. EP cancel and MP cancel, so it's equal to 1 upon root 8. So it's equal to 1 upon 2 root 2. Therefore, de Broglie wavelength of alpha particle is the de Broglie wavelength of proton divided by 2 root 2. Divided by 2 root 2. And this de Broglie wavelength of alpha particle as a proton is given the lambda 0. Therefore, lambda 0 upon 2 root 2 is our answer. Again, a proton accelerated by the potential difference 100 volt, having the de Broglie wavelength is lambda p or lambda 0. Alpha particle accelerated by the same potential difference. So what should be its de Broglie wavelength? We know that de Broglie wavelength lambda is equal to h upon p. So it's equal to h upon under root of 2mqb or the 2mev. Here the voltage are same for the proton and alpha particle. Therefore, voltage 2 and h are constant. So we can add that lambda is inversely proportional to the square root of m into q. For alpha for proton, lambda p proportional to the 1 upon under root of mp into ep. And for alpha particle, wavelength of alpha particle proportional to the 1 upon under root of m alpha e alpha. Now we know that mass of the alpha particle is 4 times the mass of the proton, and charge of alpha particle is double than the charge of proton. We substitute in this ratio, so we obtain lambda alpha upon lambda p is equal to 1 upon root 2, 1 upon root 8 is equal to 1 upon 2 root 2. Therefore, de Broglie wavelength of alpha particle is equal to de Broglie wavelength of proton divided by 2 upon root 2. Clear? Very easy, very nice. Now next. when the monochromatic light of frequency f1 is incident on a surface, stopping potential is V1. When the same surface is incident with the light of frequency f2, stopping potential VB. What should be the stopping potential? That means what is the value of the stopping potential V? For that purpose, we know that stopping potential EV1 is equal to HF1 minus phi, and EV2 is equal to HF2 minus phi. We take the difference of these two equations, EV2 minus EV1 is equal to subtraction of right hand side HF2 minus phi minus HF1 minus plus phi. Phi cancel, is common, F2 minus F1. While on the right hand side is taken common, V2 minus V1. Therefore, V2 minus V1 is equal to H upon E, F2 minus F1. We require the stopping potential when the radiation of the light frequency F2 is incident. Therefore, stopping potential V2 is equal to V1 plus H upon E, F2 minus F1. As we take the V1 on the right hand side, it becomes the positive. Therefore, V2 is equal to V1 plus H upon E, F2 minus F1. There is our option A. Right? Again, the stopping potential, or from Einstein's photoelectric equation, half m square maximum is equal to HF minus phi is equal to EV0 over the EV. We are using this concept EV1 for frequency f1, stopping potential is V1. Therefore, EV1 is equal to HF1 minus phi, and for frequency f2, stopping potential is V2. Therefore, EV2 is equal to HF2 minus phi. Take the subtraction of these two equations. EV2 minus EV1 is equal to HF2 minus phi minus HF1 minus plus phi is cancelled. Therefore, this side is common, V2 minus V1. Left hand side H is common, F2 minus F1. Therefore, V2 minus V1 is equal to H upon E is equal to F2 minus F1. Therefore, V2, stopping potential when the frequency F2 is incident, is V1 plus H upon E, F2 minus F1. Okay? Okay. After that, next question asked in 2007. For a given metal, work function is W0 and threshold wavelength is lambda. If the metal has the work function is W0 by 2, then threshold wavelength will be. So when the work function W0, at that time the threshold wavelength is lambda 0. When the work function W0 dash is equal to W0 by 2, at that time what is the lambda 0 dash? So we know that the same equation, work function phi is equal to C upon lambda 0. So here the phi, actually there is denoted as W0 in this equation, therefore it's C upon lambda 0. And new work function W0 dash is equal to HC upon lambda 0 dash. We take the ratio of these two equations, W0 upon W0 dash is equal to lambda 0 dash upon lambda 0. Substitute the value W0 upon W0 by 2. Because the W0 dash is equal to W0 by 2 is equal to lambda 0 dash upon lambda 0. Therefore, lambda 0 dash is equal to 2 lambda 0. As the work function becomes the half, the threshold wavelength becomes the double. Here, we are using the concept of the work function phi is equal to HC upon lambda 0. Here the work function initially given the W0. Now, the new wire function is W0 dash, at that time what should be the threshold wavelength? Therefore, W0 dash is equal to HC upon lambda 0 dash. Take the HC of these two, W0 upon W0 dash is equal to lambda 0 dash upon lambda 0. But the lambda 0 dash is given the W0 dash is given as the W0 by 2. Therefore, W0 upon W0 by 2 is equal to lambda 0 dash upon lambda 0. Therefore, lambda 0 dash upon lambda 0 is equal to 2, and hence the new threshold wavelength lambda 0 dash is equal to 2 lambda 0. Now friends, the next question asked in good set 2007. When the point source is kept 2 meters away with a distance from a photocell, the stopping voltage is V0. When the source distance is changed to 1 meter, the stopping potential will be, first we keep the source at 2 meter 20 centimeter distance from a photosensitive surface of the photocell. At that time the stopping potential is V0. When the source distance is changed to 1 meter, now what is the new stopping potential? Now listen, the stopping potential V0 depends only on the frequency of incident light, not depends on the distance. Right? Therefore the stopping potential remains same. The reason is that the stopping potential V0 depends only on frequency of incident light, not depend on distance from source. Therefore, our answer is no change in stopping potential. No change in stopping potential. Again, the stopping potential V0 depends only on the frequency of the incident light, not depends on the distance from the source. Because already we know that in characteristic of photoelectric emission, if the frequency of incident light is more than or equal to the threshold frequency, at that time the photoelectrons are produced from the photosensitive surface. To stop these photoelectrons to reach at their node, we apply the potential that is known as the stopping potential. Therefore, stopping potential depends only on the frequency of incident light, not depends on the distance from the source. Okay. Now the next question, also asked in 2007. Wavelength of matter particle is independent of which of the following quantities? First is the mass, second is the velocity, third is the momentum, and fourth is electric charge. We know that wavelength of matter wave from d to this wavelength, lambda is equal to h upon p is equal to h upon e. Therefore, wavelength is inversely proportional to the mass, inversely proportional to the velocity, inversely proportional to the momentum. But in this equation, the electric charge is not present. Therefore, wavelength is independent of the electric charge, or does not depend on the following quantity electric charge. Thus, lambda does not depend on electric charge. Here is actually the equation of the d Broglie wavelength, lambda is equal to h upon p. Therefore, h upon h from this equation, lambda inversely proportional to the mass, lambda inversely proportional to the velocity, mass into velocity momentum, and lambda is also proportional to the momentum. But in this equation, no quantity of electric charge. Therefore, lambda is independent of electric charge. Clear? Okay. Now, number of photons emitted per second from 60 watt bulb will be. Now, the 60 watt bulb radiates the energy. In this energy, suppose the n photons are present. Here the power is given the 60 watt. Therefore, power P is equal to total energy radiated in unit time. P is equal to energy radiated per unit time E upon T. If E is equal to NHM upon P. Again, the P is equal to NHM upon P. Clear? Now, the number of photons incident per unit time N upon T is equal to P upon HF. P upon HF. So is equal to P lambda upon H. P lambda upon H. And we substitute the value. So we obtain the answer is 2 into 10 is to 20 photon per second. That means every second 2 into 10 is to 20 photons are radiated or emitted per second from the bulb of the 60 watt. Again, the number of photons emitted per second from 60 watt bulb will be. So power is given, power is equal to total energy upon time. Total energy upon time. Suppose this energy in photon are present, N is equal to HF upon T. Therefore, N upon T is equal to P upon HF. Is equal to P upon lambda upon HC is equal to 2 into 10 is to 20 photon per second. Clear? Okay. Here value of lambda is 66 into 10 is to minus 8 meter. Consider this value for this numerical. The lambda is equal to 66 into 10 is to minus 8 meter. Clear this? So we obtain the answer is 2 into 10 is to 20 photon per second. Okay. After that, the next question asked in 2008, the photon having the 8 electron volt energy is incident on metal surface with threshold frequency of 1.6 into 10 is to 15 Hz. The maximum kinetic energy of photoelectron emitted will be. The photon having the energy E is given as the 8 electron volt. Now, threshold frequency F0 is 1.6 into 10 is to 15 Hz. So the maximum kinetic energy, K maximum or half m square maximum, we have to find out in electron volt. Therefore, from Einstein's photoelectric equation, half m square maximum, half m square maximum is equal to E minus phi. E minus phi is equal to E minus HF0. E minus HF0. Therefore, the half m square maximum required in electron volt, E is given in electron volt, but HF0, H is substitute the value we obtain in joule, so convert into electron volt, therefore HF0 upon E. That is in electron volt. Substitute the value, so we obtain E is equal to 8 electron volt minus H 6.6 10 is to minus 34. F0 1.6 10 is to 15 upon E 1.6 into 10 is to minus 19. That is in electron volt. If we simplify it, we obtain the answer is 1.4 electron volt. That is the maximum kinetic energy of the photoelectrons emitted. Again, the photon having the energy is 8 electron volt. Energy is given in electron volt. It inserted on a metal surface with threshold frequency F0 is given 1.6 into 10 is to 15 Hz. The maximum kinetic energy of the photoelectron emitted will be from Einstein's photoelectric equation, half m squared maximum is equal to hf minus phi or the ef minus phi. Phi is equal to hf0, therefore E minus hf0. We require the kinetic energy in electron volt. Already energy is given in electron volt. Now hf0 is in joule, therefore hf0 divided by E. So now this quantity of electric side is in electron volt. We substitute the value A minus 6.6 into 10 is to minus 34 is the value of Planck's constant X. Here F0 is given 1.6 into 10 is to 15. Divided by charge of electron 1.6 into 10 is to minus 19. We obtain the answer is 1.4 electron volt. That is the maximum kinetic energy in electron volt. After that, UV light of 200 millimeter wavelength is incident on the surface of iron. Its white function is 4.71 electron volt. What will be the value of stopping potential? We have to find out the value of stopping potential V0. Where is it? Here that is asked in 2008. The options are 0.5 volt, second is 1.5 volt, third is 2.5 volt, and fourth option is none of this. Here we calculate this numerical. Therefore, EV0 stopping potential is equal to HF minus phi. Therefore, V0 is equal to HC upon E lambda minus phi. Substitute the value H Planck's constant 6.6 into 10 is to minus 34. Since the velocity of light E 1.6 into 10 is to minus 19. Lambda is given. Ultraviolet light of 200 millimeter. Therefore 2 into 10 is to minus 7. Minus 5. 5 that means the stopping potential is given 4.71 electron volt divided by E. E cancel, therefore 4.71. So we obtain the answer is 1.5 volt. That is the value of stopping potential. Again, ultraviolet light of 200 millimeter wavelength is incident on the surface of iron. Its white function is 4.71 electron volt. What will be the value of stopping potential? Now, we have the Einstein's photoelectric equation. EV0 is equal to HF minus phi. Here the wavelength is given, therefore V0 is equal to HC upon E lambda minus phi. We substitute the value of constant HC and also H 6.6, 10 is to minus 34. C, velocity of light in vacuum divided by charge of electron 1.6 into 10 is to minus 19 lambda 200 millimeter, that means the 200 into 10 is to minus 9, or in other words 2 into 10 is to minus 7. Minus pi is given electron volt 4.71. EV divided by E cancel, therefore 4.71 volt. So as this take the subtraction, we obtain 1.5 volt. After that, the next question, there is asked 2 times 2008 and 2015. Alpha particle and butyr moves with the speed of v and 2. What will be ratio of their de Broglie wavelength? What should be the ratio of their de Broglie wavelength? Now we know that de Broglie wavelength lambda is equal to h upon m. Therefore, lambda proportional to the 1 upon mass into velocity. Therefore, wavelength of alpha particle divided by wavelength of deuterium is equal to mdVd upon m alpha v alpha. Now we know that the mass of the deuterium md is equal to twice of the mass of the proton, and mass of the alpha particle is 4 times the mass of the proton. Substitute this value, therefore lambda alpha upon lambda deuterium is equal to 2mp upon 4mp. Now, velocity of deuterium is given the 2v, and velocity of the alpha particle is v cancel, mp cancel, 2 is 4 cancel, therefore 1. Therefore, lambda alpha upon lambda deuterium is equal to 1 by 1. That means the d-Broglie wavelength of alpha particle and deuterium will be same. If their speed r, speed of the alpha particle is v, and deuterium moves with the double speed of alpha particle, and then the d-Broglie wavelength are equal. Again, here the d-Broglie wavelength lambda is equal to h upon m. H is constant, therefore wavelength is inversely proportional to the product of mass and velocity. So from this equation, lambda alpha upon lambda deuterium is equal to mdVd upon m alpha v alpha. We know that mass of the deuterium is double of the mass of proton, and mass of the alpha particle is 4 times the mass of proton. Here we substitute the value in this equation. Lambda alpha upon lambda deuterium is equal to 2mp upon 4mp, and velocity already given. Velocity of deuterium is double than the velocity of alpha particle, therefore 2v upon 2. So this ratio gives the one value. Therefore, ratio of d-Broglie wavelength of alpha particle and deuterium is our same. That means this ratio is 1. Now the next, asked in 2009, if a linear momentum of a particle is 2.2 into 10 raised to 4 kg meter per second, then is d-Broglie wavelength. Now d-Broglie wavelength lambda is equal to h upon t. H 6.6 10 raised to minus 34 divided by the momentum 2.2 10 raised to 4. We obtain the answer is the 3 into 10 raised to minus 38. 3 into 10 raised to minus 38 meter. There is the d-Broglie wavelength of a given particle. But here all options are given in nanometer. We have to convert this wavelength obtained in meter into nanometer. Therefore, we have to divide by 10 raised to minus 9. Therefore, lambda is equal to 3 into 10 raised to minus 38 divided by 10 raised to minus 9. Therefore, 3 into 10 raised to minus 29 nanometer. Again, very easy numerical. If the linear momentum of a particle is 2.2 into 10 raised to 4 kg meter per second, then its d-Broglie wavelength. Where is the equation? Lambda is equal to h upon p. If we substitute the value of h and p, we obtain the wavelength lambda is equal to 3 into 10 raised to minus 38 meter. But the answer is given in nanometer. We have to convert this meter into nanometer. Therefore, divided by 10 raised to minus 9. Therefore, answer is 3 into 10 raised to minus 29 nanometer. So, our option A is right.